So the expected value of a product. Okay. So let's consider a dice roll. So you roll a die and you get a roll. Let's call that x. So that's a random variable x. And we might ask, what's the expected value of x squared, which is the expected value of x times x, which is a product. So we might think, oh, using the analogy with the theorem we proved, this is going to be the expected value of x times the expected value of x. Okay, question mark, which would be 3.5. So the expected value of a dice roll is 3.5, 3.5 squared. And the answer is no. So it's not. So now, you can read the text about this, but I encourage you to now compute the expected value of x squared, from, we know the PDF of x. Okay, so it's going to be x squared weighted by the probability of that x. So this is going to equal, it's actually equal to 1 over 6 times 1 squared plus 2 squared plus up to 6 squared. And compute it, you see it's not equal to 3.5 squared. On the other hand, if you roll 2 dice, okay, and so now you've got, the roll on the first die, which is x1, and the roll on the second die, which is x2. And so in a similar way, we could ask, what's the expected value of x1 times x2? Okay. Now, if we do this from the possible, outcomes x1 and x2, so the possible outcomes are 1 through 6, so there are 36 possible outcomes. Okay, if you go, it'll be this, from the definition of the expected value will be, 1 over 36 times, 1, so x1 can equal 1 times x2 can equal 1, plus 1 times 2, plus 1 times 3, plus 1 times 6, okay, plus 1 times, plus 2 times 1, plus 2 times 2, plus 2 times 3, plus 2 times 6, okay, plus 3 times 1, plus 3 times 2, plus 3 times 6, and we keep going up to 6 times 1 plus 6 times 2 plus 6 times 6. Okay, so that's the expected value of the product of 2 independent dice. And if you compute this, you'll see that this is 1 over 36. I can factor out the 1, 2, 3, 4, and so on up to 6. And I get 1, 2, 3, 4, and so on up to 6. So this is 1 over 36. 1 plus 2 plus 3 plus up to plus 6 times 1 plus 2 plus 3 plus up to 6. Okay, because I have 1 times 1 up to 6, 1 times 1 up to 6, 2 times 1 up to 6, 2 times 1 up to 6. So you can work out this algebra, okay? But you'll see that this is exactly equal to 1 over 6 times 1 plus 2 plus 3 plus up to 6 times 1 over 6 times 1 plus 2 plus 3 plus up to plus 6. I just broke up the 1 over 36 into 2 1 over 6s. But this is exactly the expected value of x1. And this is exactly the expected value of x2. Okay? And so this is the expected value of x1 times the expected value of x2. And wow, the expected value of the product is the product of expectations. So sometimes it works, sometimes it doesn't work. Okay? And one way in which you can be sure that it works is when you're taking the product of independent random variables. Product of independent random variables. Okay, so independent random variables are typically arising when they are the random variables that are coming from measurements of totally different, totally independent experiments. Like you roll one die and then independently roll another die. So 2 totally independent measurements. Okay. And so you can read the text about more details. So the expected value of a product is only the product of expected values for independent random variables. Okay, we're going to move on to show you some techniques that use the law of total expectation, and then we want to introduce indicator random variables. Okay, so let's talk about total expectation and build up expectation.